All right, so we now know some names for some shapes of molecules when you have a known number of regions of electron density on the outside of it. For example, I look at a chemical like CH4. I see I have a central atom with 4 outside atoms, 4 regions of electron density, and that results in a tetrahedral shape, right? I'm familiar with that. We learned that from the previous slide here, tetrahedral, right? We can also have regions, so this is central region and 4 bonding regions, right? 1, 2, 3, 4. We can also have situations where I have a central region and 3 bonding regions, but a 4th non-bonding region. Or I can have a central atom, 2 bonding regions, and 2 non-bonding regions. All of these will have a tetrahedral shape in terms of the regions of electron density. But if some of those regions are non-bonding, then the actual molecule shape is only considered to be where atoms are. And so if I have one region of electron density that is non-bonding on a tetrahedral shape, 4 regions of electron density, I get this, what we call trigonal pyramidal molecular shape. Central atom, 3 atoms below that come together to form a pyramid with a trigonal base. 2 regions of electron density that are non-bonding and 2 that are bonding result in a bent structure.
It looked linear to me.
Oh, you mean this down here?
Yeah.
Well, see, we have to be careful how we draw things on a 2-dimensional surface. I mean, or we have to realize that once we've drawn it, it doesn't mean that that's the actual shape, right? You could say that is linear, but let's look at a molecule in 3D and understand what's going on. So for an example here, I have a molecule of water, all right? Here's my molecule of water. There's a oxygen and 2 hydrogens. If I line it up like this and somebody shows me and asks, what's the shape of this compound? I might be tempted to say it's linear, right? But what I really need to do, what you're looking at and how you see it isn't the determination of whether it's linear or not, or whatever its shape is. What determines its shape is the number of regions of electron density and our understanding of the different shapes that result when you have that many regions of electron density around it, okay? So what we're looking at here is if I have a 4 regions of electron density and 1 is non-bonding, the resulting shape is trigonal pyramidal. If 2 are non-bonding, the resulting shape is bent because the 4 regions still attain this tetrahedral shape, but the molecular portion is now bent. Now, what do you think? Do you remember the angle between the 4 regions when you have 4 regions? Oh, there it is right there.
109.5.
That's right, it's there on there. So the angle between the MX bonds in this molecule will be about 109.5. Now, it turns out that because these lone pairs take up a little more space, and we'll talk a little bit more about that later on, they take up a little more space, therefore it squeezes down this angle a little bit, and when they have lone pairs, we say that the angle between here is a little less than 109.5. If we look at something like a trigonal planar scenario, and we have one region of non-bonding electrons, the resulting molecular shape is a bent molecule with a 120-degree angle there. All right. This region of electron density takes up a little more space, so it might be slightly smaller than 120, but not much because there's plenty of room for that lone pair of electrons. Okay. Now let's look at a trigonal bipyramidal compound, 5 regions of electron density, and replace those regions of electron density, binding regions, with non-bonding regions, and see what we call the resulting compound. So this resulting compound here is called a distorted tetrahedral. This one here is called T-shaped. This one here is called linear. And notice that the lone pairs, the regions of non-bonding, preferably go to the equatorial regions. And this is because the non-bonding regions take up more space. The bonding regions, as the electrons stray, they can be sucked in by an atom on the other side of the bond. But non-bonding regions have nothing to kind of contain them on the other side, and so they take up much more space. And for this reason, non-bonding electrons will always go to the place where there's more space for them, which in a trigonal bipyramidal compound is in the equatorial locations. All right. Now, in the case of octahedral geometries, we said, I don't know if you remember, but octahedral, there is no region here that has more space. All of them are the same in terms of how much space they have. So it doesn't matter where your lone pair region will go. They'll try to go opposite each other when there's a second, but yeah, it's not preferentially, because there's no axial or equatorial locations. They're all the same. They're all degenerate, we say. So the resulting structure here is called square pyramid. And I think it's kind of obvious, that we have a, where were we at? We have a tetrahedral, right there. We have a square pyramid, right? If you have two regions of non-bonding electrons, then we call that square planar, okay? So it takes a while to maybe kind of remember these, but after you see the names, then they just kind of explain themselves, right? This is a square pyramid. And also, in reality, these names are not always, not always used. So some people might have slightly different names, but still it's just going to describe the structure of the compound, the shape of the compound. All right, so here it is. We have a compound here, and we want to know the molecular geometry for this compound. All right, this is ammonia, NH3. The first thing we do is we identify the number of regions of electron density around the central atom. Okay, how many regions of electron density are around the central atom here?
4.
That's right. We already saw that earlier on, right? 4 regions of electron density around the nitrogen. 1 bonding, 2 bonding, 3 bonding, and the 4th non-bonding. Okay? So if we just think about those 4 regions, okay? So here's central atom, 4 regions, and this time I'm not going to draw them as bonding or non-bonding. I'm just going to draw them as 4 regions. Okay, so let's say there's 1 region up, 1 region down, coming at us a little bit, 1 region going away from us in the plane, and then another region right there. So I have 4 regions of electron density. Okay, what shape do those 4 regions attain?
You mean what's the shape of the molecule?
No, if I have 4 regions with 1 central atom, 4 regions coming off, what shape is that?
That's tetrahedral.
Very good, tetrahedral. And that's then the shape, not of this molecule, but of these 4 regions. Now, if I take one of those regions and I change the it to a non-bonding lone pair, then what's the resulting shape of the molecule?
I can't remember what that was.
Well, see, it looks like a what on the bottom?
A triangle?
Looks like a triangle on the bottom, and it's forming a pyramid from that triangular base. So this is called a trigonal pyramid. Trigonal pyramid. All right, so trigonal pyramidal. Okay, how about this one here? What's the shape of this one?
Is that linear?
Okay, no, it's not linear. But before we just jump right into the shape, what is it we want to do?
Oh yeah, we want to find the regions of electron density. There's 4 there.
Okay, very good. So around the oxygen, I have 4 regions of electron density. So because I know that I have 4 regions, then I know that the shape that it attains, again, is what? What's the shape of all these regions? What shape do they adjust themselves to?
Tetrahedral.
Very good. And now if I have 2 of those regions, so here's my tetrahedral shape. Now if I have 2 of those regions, let's say this one on top and this one on the side, I'm going to turn into lone pairs. Then the resulting shape will be what?
Oh, bent.
Very good. Bent. Now, the other thing we need to know along with what the shape is what's the angle between the bonds or the non-bonding regions. So what is an angle between non-bonding regions in a tetrahedral shape?
Is it 109.5?
Very good. It's 109.5. 109.5 is our angle between bonding and non-bonding regions in a tetrahedral shape. Okay, so what would you say then is the angle between these water molecules here? Or sorry, so this is a oxygen and this is a hydrogen. Between the hydrogen-oxygen bonds and the water molecule, what would our angle be?
Is that 109.5 too?
It is. It is. 4 regions of electron density. Now, it's a little less than 109.5 because it turns out that these regions here, the lone pair regions, take up a lot of space and kind of squeeze down this angle. So it's what we say is a little less than 109.5. But it's bent, right? It's bent. All right. How do we know what the shape of this is here?
Well, it looks bent.
Okay. And that's what we got to make sure we don't fall in the trap of doing. Just looking at it and saying, this is what it looks like. Because like this one looked linear, right? They're going to make pictures confusing for us to see if we are learning how to identify the shape of a molecule the correct way. Which in this case, we need to again identify the number of regions of bonding and non-bonding electrons around the central atom. So how many regions there, Fred?
2 bonding and 3 non-bonding. So is that 5?
That's right, 5 regions. 1, 2, 3, 4, and then 5. Do you remember the shape that those 5 regions are going to adjust themselves into?
I can't remember.
All right. So if we look back here, let's go back a little bit. Here's our 5 regions, right? And we see that it's trigonal bipyramidal.
Okay, yeah, trigonal bipyramidal.
Very good. Trigonal bipyramidal. Now remember, we can look back at this one as well. When you have trigonal bipyramidal, the non-bonding pairs want to go to which region? What do we call this region?
That was the equatorial, right?
Yeah, the equatorial region. Now remember why they want to go there?
Because they take up more space.
Very good. So here we have 5 regions, 3 of which are non-bonding and 2 are bonding. So let me see if I can sketch something that looks familiar to us. 1, 2, 3, 4. So there we have 3 equatorial and 2 axial, right? And on the equatorial positions, we're going to put the non-bonding. How many do we have?
3.
So 1, 2, 3, and then we have the bonding regions here. Okay? Does that make sense?
Yeah, so is that thing, what do you call that shape?
Here, let me fix my little thing here a little bit. There we go. That shape is, the other iodine is there. It's just linear, right?
Yeah, okay, I see that.
3 regions of non-bonding electrons on the equator and 2 bonding iodines from the central iodine, right, in axial positions. Okay, very good. How about this one over here?
CH4, that 4 regions, that's just no non-bonding. That's just tetrahedral, right?
Very good. Tetrahedral. Good job. What's the angle between these 2 hydrogens?
Well, it looks like 90, but it's really 109.5.
Very good. 109.5. Looks like 90, but 109.5 is the angle between the regions of electron density in a tetrahedral molecule. Okay, what about this one here?
Do double bonds count as 1 or 2?
Double bonds count as a single region of electron density, so there's just 2 regions.
Yeah, so that's just linear.
Very good. Linear. Fabulous job.